Okay, so today I'm going to give a brief introduction to the software SCAPS 1D. It is basically used for simulation of solar cells. So after installing, you should open this. Here is the graphical user interface, the application. So first I will show you the basic interface of this application. Here is the environmental temperature, the work temperature, that is. And here is the frequency. We need not touch this as of now. And here are the series and shunt resistance. Normally, we turn this off. I mean, you should keep it as it is. And here is the illumination option. Now it is dark. So if you turn it, you will now have to select the spectrum file from here. So normally for research work or other applications, we use the AirMass 1.5. That is, if you select from here, this is the this option, Sun SP. Okay, so always remember that this option is turned on and this is selected. Now here are the options that you will have to select for plotting. If you want to see the IV characteristics, you will have to tick this. If you want to see the quantum efficiency in terms of wavelength, you will have to tick this as well. Here are the starting and ending values of the y-axis, the voltage values. Normally, we should keep this a little bit higher, like 1.8, say, and tick this. Otherwise, you will get convergence error if you do not tick this option. Okay, now let's get into a problem. Click this set problem. Let's try to build a structure first. If I show you from a paper, normally in each and every paper, there will definitely be a table with these properties. You should definitely cite the paper after using these values. Okay, so basically you can just import these values and build the layers, the interfaces, and simulate this solar cell. It's not that much hard. If I show you the options, like if you click this add layer, see the band gap. Here is the band gap value. The thickness, here's the thickness parameter. Micrometer, you can just use 0.5. You can also change it to nanometer as you want. Here is the electron affinity value. Let me, okay. So you will find all the parameter values from the respective paper, and you will just have to put these values in it. Like the conduction band effective density of states, the thermal velocity. Normally, the thermal velocity is always kept at 1 in 10 to the power 7. You should not change it. Here are the electron and hole mobility. This should remain as it is. No need to tick this. If I load a similar material that I built earlier from another paper, okay, let's say this one. Okay, So I took this data from a paper, and if I try to add defects, it is already okay. Let me remove this. Let me add a defect. This is the bulk defect of the absorber layer. This is an absorber of perovskite solar cell. So click this. Here you can set the value of the total defect density of the bulk material of the absorber layer. So normally you should keep this between 10 to the power 14 to 10 to the power 15. So let's keep it 10 to the power 14, and no need to change anything else. Click add. So after you put the values from a paper into this box, you will get sorry. After you add these defects, now you will have to save this material. Save. So for saving a particular material, if I say that if I change the value, okay, okay, let me show you with this example. Click this save material, tick these things, hit OK. Now you can give it any name. In my case, if I type methyl ammonium tin iodide, say dot material, it should this extension should be used, otherwise it will not be saved under this folder. Now click save. Okay. After saving this, say that you want to add this layer now. Okay. So you can now load the material that you saved earlier. Click just load and try to find this. Here it is, the methyl ammonium tin iodide material. Just click this. Okay. Done. The addition is done. Okay. So in this way, you can design different ETL, that is electron transport layer, hole transport layer, the glass electrodes, and this absorber layer. If I load a similar structure I designed before, okay, let's load this. Here it is. So this is the HTL, hole transport layer. This is the absorber layer that we designed earlier. This is the electron transport layer, and this is the glass electrode. Normally, the back electrodes metal work function, after you unclick this, you will get the option to change its value. Normally, it's kept at 5.1 for gold electrode. So let's keep it 5.1. The higher the value of the work function of back electrode, the better the efficiency we will get. And if I talk about the hole transport layer, here is the hole transport layer, cuprous oxide for this particular paper, and this is the electron transport layer. This is these two are our absorber layer. This paper actually implements a double absorber. That's why we are seeing here two absorber layers. Let's forget this, just showing you this. And this is the FTO glass layer. It is needed for implementing the electrode at the front side, this side. And light should be illuminated from this side. So definitely the glass electrode should be transparent. That's why it's called glass electrode. And you can change the illumination from left to right or right to left, but you should always remember that the illumination should be from the transparent side. Okay. And as for the apply voltage to, this might be quite misleading. Let me explain this in a very easy way. Here is our absorber material, and after back electrode, this is our back. This is our whole transport layer, HTL, and this is our ETL. HTL, ETL. HTL means it is a p-type material. So we know that after the junction formation, there are some exposed negatively charged, some negative charges at the interface. So after the absorption of light in this absorber layer, the photo-generated electron and holes, the holes will be attracted to this HTL side because of the exposed negative charges at the interface between the absorber and HTL. As a result, the holes will be accumulated here in a great amount, and similarly, electrons will be transported to the ETL layer due to the attraction by the positive charges that are exposed due to the junction formation between absorber and ETL layer. That's why we are saying that this portion is positively polarized and this is negatively, I mean, grounded. This is the explanation for this option. There is no application of voltage because we know that solar cell itself acts as a battery. We need not apply any voltage to solar cell. Okay, so I have shown these basic things, but here is another important option, that is the interface. We should always set the interface defects before simulation. If you click this, you will see this interface option is between 1 and 2. Always double check which are 1 and 2. If you click this, this is the layer 1 and this is the layer 2. Let's see. Okay, this is HTL and absorber. Okay, the naming is okay. At first, you will see empty here. If you click this box, you will get this option. You can change it to 10 to the power 10 or 11. Let's keep it 10. This is the standard 10 or 11. You cannot decrease the interfacial defect below 10 because that will be too much impractical. Okay, keep it realistic as you can do. Yeah. So, okay, accept. Here is a thumb rule for the interface between the absorber and ETL layer. The distribution should be Gaussian here. In earlier cases, it was single. I will revisit that, but you should always click this Gaussian for the ETL and absorber layer interface. Okay, let me show you. Here it was single. Okay, for other layers it is single. Here it's also single. Okay, so Gaussian should be used for only the interface between ETL and absorber. So let's now move to simulation part. After setting all the parameters, let's see if I have missed any point. You should not change anything for the absorption. Keep it as it is. No need to change anything. Okay, for beginners, it's okay. Let's see. Let's just check if we have missed anything. Okay, we are good to go for simulation. After setting all the values, click. Oh, yeah, you should save the material for future use. So click save. If I say just new dot def, okay, see it is saved. See if we can load it. Yeah, we can load it easily. Let's check it if we can load it. Click new, everything is gone. Click load. Now click this new def that you have saved earlier. Yeah, here it is. So it's very easy to set the parameters and build this perovskite structure. Click OK. Now the simulation part. Okay. So for beginner level, we'll just do a simple calculation for getting the VOC, the short circuit current, the open circuit voltage, the fill factor, and efficiency. Click the single shot here after taking this and keep it a little bit higher. As I said earlier, click single shot, and now you'll have to wait for a while. Okay, it's finished. Click here, the IV. Well, we can see here that the efficiency here is 31.88%, which is quite good. Okay, for perovskite cell other than lead material, it's very much high. Okay, here is the VOC, the ISC, the fill factor, the efficiency. Here is the curve. You can take the absolute value. Okay, and if you want to extract data from this curve and use it in some other software like Origin or MATLAB for further processing data, you should simply just click show. Here is the values. Okay, you see all the values here. You can simply copy all the values. Okay, think everything has been going. Click Control C, and then just open an XLS file for saving the data first. Click Control V. Okay, here it is. Everything has been collected. The data has been extracted from this software. Then you can copy this and put it in Origin or other software for further processing as you wish. Okay, very simple. If you see the quantum efficiency curve, okay, we used the 1.5 air mass, and we can see that for approximately this region, the efficiency is highest. Okay, so it varies with wavelength. It will be useful later while researching more. It's not of that much importance as of now. You can select a specific wavelength of light application from here. Okay, I'm not showing this. Okay, now a basic question, like if I want to say vary the thickness. Okay, if I want to, shit, it does. Okay, let's wait. If I want to vary the thickness, say, of the absorber material and see at which thickness we are getting the highest efficiency value. Okay, so to do that, please keep up with me. Follow the steps that I am doing. Click OK, and here the batch setup option. Okay, click this, click add. Here you will get all the layers and also the interfaces as well. We want to vary its thickness. Okay, this is the absorber. You can also vary its defect density, the band gap value, electron affinity value. All the parameters can be varied. It's very simple process. So for thickness variation, click this. Now say I want to vary from 0.5 micrometer to 3 micrometer. And the steps say I keep it like 15 steps. Just get an idea. That's it. Now click this record setup. Here the IV characteristics, all cell, okay. Click this insert above option. Now these two are not that much needed. Click remove, remove. If you just want to view the eta, that is efficiency, you can also delete this. I am keeping this. Okay. Now, just click this, click calculate recorder. You'll have to wait until all the 15 steps has been calculated. Let's wait for completion. Taking a lot of time, too much steps. Should have kept it under 10. Yeah, it's done. So now click on recorder option. Here you can see that with the variation of the thickness of the observer layer, the efficiency increases. Okay. To get a better view, if we again, but it will take a lot of time. Let's show this. Batch setup from say 2.8 to 6. Make it 7 steps. Okay. Let's run this again. It's completed now. Click on recorder. Well, uh, now we can see that after 2.8, okay, if we increase the thickness further, initially we saw that from 0.1 micrometer up to 2.5 or something, it was increasing. But after 2.8 to 6, it's decreasing because, like if the length of the observer is too high, I mean the thickness, the distance between the HTL and ETL, the recombination rate will get higher. That's why this is decreasing. So this is the eta curve. If you want to view the VOC, here it is the open circuit voltage curve, the short circuit current curve by varying the thickness or the fill factor. Okay. So this is how you can do the sweeping operations here and choose the optimized value for of the parameter of any layer, like for thickness or defect density or the doping values as well. Now, let me show another thing. You can clear the old simulation cards from here. Clear all simulation. Everything will be cleared. If I want to show the script setup for tandem cell simulation. So what is tandem cell? We know that tandem cells are basically a stack of cells. Okay, stack of mini structures. If I say that there are two structures and the light is illuminated from one side, the illumination side material should be of higher band gap, and then the light will cross through the lower band gap to the back electrode. For script setup, okay, let me first show you the loaded files. Okay. For tandem cell simulation, I have already created two cells. The top cell, okay, this is the top cell, and its band gap is 1.5, high band gap, okay. And I have also created a bottom cell as well, okay. Its band gap is lower, as I said earlier. It's a stack of cells with variation in band gap, okay. Now here in tandem cell simulation, we need to create a link between the top and the bottom cell, between two structures, two separate structures, to simulate it all together. To do that, click OK. Here, click script setup and click this load option. Here, tandem. Okay, here it is. Tandem connection.script. The script I have collected it from internet. Okay, this is a general file. So earlier I showed you that the names of my tandem's top and bottom cell, top.dev and bottom.dev. So in script file, you should keep this in mind and rename this here. Okay, top.dev. If something else is written, you should write it like this, the same way you have defined your files, bottom.dev. Okay, so if you now click OK and click execute script, the U value. One minute. Okay, here the X value is the voltage VOC. The Y values are the short circuit current values, and the Z value, these indicate the fill factor. The U value here indicates the efficiency of the whole tandem cell. Okay, if you click continue, here is the curve for the tandem, and you click this and click refresh. So this is the overall curve This is for bottom, I think. Let's verify. Yeah, this was the green is bottom. The blue is for top cell. This is for bottom cell, and this is for the overall stuff. You should keep in mind, though I have simulated this structure, I have not done the current matching step. You should do it. I am just showing you how to execute the processes for simulating the tandem cell structure. Okay. So I think I have covered the basic stuffs about this software. This is a pretty much cool software. And always remember to keep this off, okay? At no position. And the temperature, the room temperature, okay? Ideal condition from temperature. So that's it. Thank you for your valuable time.